Statistics and Mechanics, Advanced Subsidiary Paper 2, 8 MAO. You should show sufficient working to make sure your answers and methods are clear. Answers without working may not gain full credit. Wednesday, 23rd May 2018. Question number 1. A company is introducing a job evaluation scheme. Points X will be awarded to each job which based on the qualification and skills needed and the level of responsibility. Part A, describe the correlation between points and pay. So since y is equals to 4.5x minus 47 has a positive gradient, the gradient is plus 4.5, therefore it's a positive correlation. As points increase, pay increases. So it's a positive correlation since the gradient is positive. Part B, give an interpretation of the gradient of this regression line. It is the extra point. It says every extra point gives £4.50 more on the pay. So every extra point gives £4.50 more on pay. So it's pounds per point. So it's like a rate. Pay, pounds on the y-axis, points on the x. So it's the pay or pounds per point, which is a rate. Question 1C. Explain why this model might not be appropriate for all jobs in the company. So y equals to 4.5x minus 47. For points less than 11, it would give pay which is less than 0, which is ridiculous. Negative pay. For n less than 10.4, it would give negative pay, so not suitable. And you can see how we got 10.4 from that. When you plot the straight line graph, y equals to 4.5x on the graphics calculator, it crosses the x-axis at 10.4. So when n is below 10.4, you will get negative pay, which is not suitable. So you don't know the range of points used to find the regression line. So a small sample of size 8 may not be representative to cover all the jobs. And that's the view window which you use to see all the details. So x is 10.4. That's the root where it crosses the x-axis. And that is where, if n is less than 10.4, it would give a negative pay. Question number 2. A factory buys 10% of its component from supplier A, 30% from supplier B, and the rest from supplier C. It is known that 6% of the components it buys are faulty. Of the components bought from supplier A, 9% are faulty, and of the components bought from supplier B, 3% are faulty. Find the percentage of components bought from supplier C that are faulty. So the best way is to represent this on a tree diagram. So we have components A, B, and C. So 10% is same as 10 divided by 100, so it's 0.1. 30% is 0.3. And so 1 minus 10% minus 30% gives you, so 100% minus 30% minus 10% gives you 60%. So this one is 60%. So here it is 100%. And for A, 9% are faulty. So it's 9 divided by 100, which gives you 0.09. So 9% are faulty. And we don't know how many are not faulty. For B, 3% are faulty, which is 0.03. And how many are not faulty? 1 minus 0.03 which gives you 0.97, the probability. And for C, P for faulty and 1 minus P for not faulty. So with the tree diagram, one, the probability of faulty, given that it's from C. So we can use 0.1 times 0.9, if we go down that way, plus 0.3 times 0.03, plus 0.6 times P. So we're following those yellow branches and we're multiplying them. So 0.1 times 0.09 plus 0.3 times 0.03 plus 0.6 times P. All of that should be equals to 0.06, because it says 6% of the components it buys are faulty. That's how I got 0.06. So when you work all of this out, you will get 0.018 plus 0.6 times P is equal to 0.06. Now 0.6 times P, if you 0.018 to the right, it becomes minus 0.018. And times 0.6 comes to the right, it becomes divided by 0.6. And you do that in your calculator, you get P to be 0.07. And to change to percentage, you times by 100%, it gives you 7%. So it says find the percentage of components bought from supplier C that are faulty. We would say it's 7%. Question 2b. A component is selected at random. Explain why the event the component was bought from supplier B is not statistically independent from the event the component is faulty. For independent events, probability of A and B is the same as probability of A times probability of B. So for independent events A and B, probability of B given A is equal to probability of B. Probability of A given B is equal to probability of A. Probability of A intersection B is probability of A times probability of B. So from the tree diagram, the probability of supplier B intersection faulty is 0.3 times 0.03, which gives you 0.009. And probability of supplier B times probability of faulty is 0.3 times the probability of faulty is 0.06. That gives us 0.018. But you notice 0.009 is not the same as 0.018. Therefore, the events are not independent. So it is written down here neatly. Probability of B and F is 0.009. But probability of B times probability of F, it gives you a different answer. 0.3 times 0.06 is 0.018. These are not equal, so they are not independent. Unless otherwise indicated, wherever a numerical value of G is required, use 9.8 meters per second squared and give your answer to either 2 significant figures or 3 significant figures. Question number 6. A man throws a tennis ball into the air so that at the instant when the ball leaves his hand, the ball is 2 meters above the ground and is moving vertically upwards with speed 9 meters per second. The motion of the ball is modeled as that of a particle moving freely under gravity, and the acceleration due to gravity is modeled as being of constant magnitude 10 meters per second squared. The ball hits the ground t seconds after leaving the man's hand. Using the model, find the value of t. Right, we're going to be using the Seward equations. So these are the equations down here. V equals to u plus at, and s is equals to that v squared. S equals to ut plus half at squared. S equals to vt minus half at squared. Those are the equations we're going to be using them. So it's very important to list them down as such. So for question number 6, we want, that's when you start throwing the ball at that height of 2 meters above the ground, and that's the ground level, and it goes to the top and it comes down. Going up is positive, so the initial speed is 9 meters per second. And if that's where you start when you first throw it, and that's where it ends, the displacement is minus 2 meters. That's why we have displacement is minus 2 meters, because it's below, and going down is negative. So it's minus 2 meters. Initial speed is 9 meters per second, and it is positive because we said going up is positive. Final speed, we do not know. Acceleration is minus 10, and it's giving us 10 meters per second in the question, but it's minus because acceleration is acting down, and we have t. We want to find when t equals to capital T. So it's acting down, and acceleration is pointing, going downwards. So we want to find the time. So we want to use an equation that has no v in it, because we don't know what v is. So want is something that has no v, but it has t in it. So this one has t, and it has no v in it. So that's the one we're going to use. So S, displacement is minus 2, because going up is positive, and the thing is minus 2 down. S equals to u, tu is 9 meters per second. We write t as capital T, plus half times minus 10, because it's coming down, so it's negative, times capital T squared. Now, minus 10 divided by 2 is minus 5. So we can take the minus 5t squared to the left and the 9t to the left. So it becomes 5t squared minus 9t minus 2 equals to 0. When you factorize, you get 5t plus 1, t minus 2 equals to 0. So 5t is equals to 0, or t minus 2 equals to 0. So we have 5t equals to minus 1. So t would be minus 1 over 5. We'll reject this because we want the time to be bigger than 0. T minus 2 equals to 0. So that means 2 goes to the right. T becomes equal to 2 seconds. So it says find the value of t. T is 2 seconds. Question number 7. A train travels along a straight horizontal track between two stations A and B. In the model of the motion, the train starts from rest at A and moves with a constant acceleration of 0.3 meters per second squared for 80 seconds. For this model of the motion of the train between A and B, state the value of the constant velocity of the train, state the time for which the train is decelerating, and sketch a velocity time graph. So we're going to be using these Suvart equations at the bottom. So it's good to note them down. So we'll first of all write Suvart. The displacement, we don't know that. U is equal to 0 because it starts from rest at A. So it starts from rest at A. V, we don't know. Acceleration is 0.3 meters per second squared. That's it there. And time is equals to 80 seconds. That's it there. So we use V equals to U plus 80, this first one. We know U is 0. Acceleration is 0.3. And T is 80. So that will give us our V to be 24 meters per second. State the time for which the train is decelerating. We write down to Suvart. We don't know the displacement, but we know the initial speed now is 24 meters per second. That comes from the first part. Final speed is equal to 0 because it comes to rest at B. So the final speed is 0. Acceleration is minus 5 meters per second squared because it's decelerating. So we use V equals to U plus AT. You make T the subject is V minus U over A. So final speed is 0 minus initial speed is 24 and the acceleration is minus 5. That gives you T to be 48 seconds. So this technique of the final speed there becomes the initial speed here. Sketch a velocity time graph. So what happens is, you see it takes 48 seconds to decelerate. So that goes there. And the first one, it goes up is to 24 meters per second. So uniform acceleration to 24 meters per second. It stays there for T. We don't know what T is. And then it decelerates for 48 seconds. So it takes 48 seconds to decelerate. The area between a velocity time graph and the horizontal x-axis represent the distance traveled. For a motion in a straight line with a positive velocity, the area under the velocity time graph up to a point T represent the displacement at time T. So we're going to use this area of a trapezium, half A plus B times the height in between. That's what we're going to be using to work out the area of that trapezium. So to work out the area, we have half of T, is that top part there. This bottom part is T plus 80 plus 48. So we're adding the two parallel sides. So that's T, the top part, plus 80 plus T plus 48 times the height in between them is 24. 24 is this value there, which is the height in between them. So that height in between those two parallel sides is 24. That's equals to 4,800. So we want to solve for T. 80 plus 48, it gives you 128. And so 2T plus 128, if you take 2 to the other side, it becomes 4,800 times 2 and divide by 24. So that gives you 400. And you minus plus 128 goes to the right, it becomes minus 128. So 2T becomes 400 minus 128. And then times 2 goes to the right, you divide by 2. So it becomes 272 divided by 2, which gives you T to be 136 seconds. So using the model, find the total time taken by the train to travel from A to B. So to travel from A in pink there to B, that there is the total time. So we want to add 80 plus T plus 48. Watch this, 80 plus T plus 48. So 80 and T is 136 plus 48. That gives you total time of 264 seconds. So this is another way to find the total time. So you know the total distance is 4,800. You divide that shape into a triangle, a rectangle, and a triangle. So you find area of a triangle plus area of a rectangle plus area of a triangle, and you add them up. So the first triangle area is half times 80 times 24, because that base is 80, that height is 24. Area of the rectangle, base times height, 24 times T. And area of the last triangle, half times 48 times 24. And that gives you 136 for T. and you will get the total time by adding 80 plus 136 plus 48. You get the same 264 seconds. Question 7C. Suggest one improvement that could be made to the model of the train, of the motion of the train from A to B in order to make the model more realistic. So your acceleration to constant velocity, then to deceleration. So your acceleration to constant velocity, then to deceleration. So either a smooth change from acceleration to constant velocity or from constant velocity to deceleration, or have train accelerating and or decelerating at a variable rate. So you want to include time to change from constant acceleration to constant velocity, and or time to change from constant velocity to constant acceleration.